Okay. So, hello, folks. Welcome to the RecSys Learning Book Club. Today, we have week 7 of our book club. Today, we'll be talking about ranking in recommendation system. It's a very important topic because that is the way recommendation system designed that which particular content we have to recommend at which position. Most of the time, like when we design a recommendation system, it has to select a candidate from thousands of catalogs to few hundreds of catalog to display on the screen. But as we know that like most of the screens have very limited viewing area, and to select like high ranked model is very important for such cases. So small introduction. My name is Rohan Singh Rajput. I am senior machine learning engineer at Headspace. If you want to connect more information about recommendation system and previous recordings, please uh, connect me on LinkedIn. Uh, so I changed a little bit the agenda. This time I dedicated more time for learning of the book. I reduced time for the discussion, and we have like a small introduction and a small wrap up. So information about the book. The book we are talking in this course is Building Recommendation System in Python and JAX. The reason we chose this book because this is one of the advanced book covers like most of the advanced topics in recommendation system. It's a highly practical oriented book with a focus on building production level system, and it's written by industrial professional who have a hands-on experience in building real-time recommendation system. So today we'll be talking about chapter 8. Chapter 8 contains two important category of rank-based recommendation system. First, we know as feature-based, and another is known as counting-based. And we'll know that like how these two types of recommendation system help us to rank the content. So first, we'll talk about the feature-based recommendation system. In the feature-based recommendation system, the important class of that recommendation system is called bilinear factor models. These models are used when we are using feature of our user and items. And let's go more deeper into it. So the objective of any recommendation system is to obtain a ranking RIX from user I and item X. Here we are using I as a for the user and X for item. Previously, if you know that we were using I as an item and X for the user, but this in this particular case we are like flipping. We will be using I as a notation for user and X notation for the item. Now, what we are trying to do, our objective is to find out a way where using the feature vector of item and user, we derive those ratings. So this is what we want to do. For any unknown item, based on the user feature and item feature, we want to derive this rating. And this is the entire objective of recommendation system. Now, to derive that, we have to find out some kind of similarity score. Similarity score help us to find out that which particular uh, user vector is similar to which item vector. And to take a small example, so here we are talking all about vectors. Vectors is some kind of representation of user personality and item characteristic. It's very important to understand that whenever we talk about recommendation system as a user feature provide some kind of personality information of user or profile information of user, and item vector derive that what are the different characteristic of that item. So based on that similarity score, we can use this similarity score IX, where we are using a dot product between vector I and vector X and normalizing with their magnitude to just overcome any kind of popularity bias or any kind of like here we are just trying to normalizing it to get like equal equal weightage for all polarity and vector. So in bilinear factor model, this is like a little bit more maths here. What we are trying to do, uh, will obtain a rating from this similarity score based on these expression. So in this particular expression, suppose we have like k features of item I and uh, not vector I and vector x. So we will be using a summation of dot products between I and x for k k embedding, or k is like dimension of those feature vectors. Now here what we are trying to do, we are trying to decompose this matrix into uh, uh, other metrics, because we want to know it, we want to have some kind of learnable parameters, and those learnable parameters will help us to obtain the rating based on the feature and item vector. So here we are defining a of k, which is a matrix that will help us to obtain those learnable parameters. And these learnable parameters usually help us to obtain like future uh, ratings of item and user. Like so, now we can further change this expression to a particular set of dimensions. So suppose we are talking about n number of users having k number of dimensions. So what we can do, we can further break it down into this matrix form. Here we are using a more general representation of vector, where we are obtaining this I of kl, ik, and xl, these different vectors to represent all the user and item features along with the learnable parameters. Now, if you see clearly what we are trying to do, we are trying to decompose it into this matrix form. This matrix form gives us a lots of advantage, because if you see more closely, this will help us to uh, uh, this will help us to derive this equation as a linear regression. And once we convert into a linear regression, then we know that there is a optimization solution present for linear regression problem. We can use those optimization solution to obtain our learnable parameters. The entire objective here is to convert this equation into uh, a linear regression method, where we can use like a least square or some kind of different optimization to obtain the solution of those learnable parameters. The name suggests here it is a bilinear factor model, because what we are trying to do, these are like two linear linear variables here, like xi and xk, and we are trying to convert into a linear regression method. So again, uh, let's say this vector I xt belongs to Rnm, where we can further decompose it into these two vectors. As we have seen previously, that we have put this matrix into this form, where we have I a x, and here a is the learnable parameter, and now we can equate to this I x transport as a vix, and vector a as a beta. And now if you see closely, now we have converted this equation into a linear regression method. Now we have a beta constant along with the, not a beta constant, it's a weightage parameter multiplied by the variable vix. And vix represent the vector interaction between item and the item in the user vector. So uh, the important question here is that when we do this kind of embedding, does it mean that our user space is same as the item space? We are converting everything to the vector. Should we visualize it as a three-dimensional space, where we are using user space and item space and different vector? Actually, it's more complicated than that, because When we do such kind of changes, we have to make sure that we are not confusing it with the Euclidean space. uh, the reason here is that uh, sometimes they have shared latent space. That means that on a higher dimension, there could be a different type of interaction there, which is not captured by easily like in 3 dimension. In the higher dimension, it's much more complicated case. We have to make sure that we have a consistent definition between the distances. That means that on a higher level, you think that like if we think this is a user vector u, right, and this is the item vector I. Now, in the 2D space, it's very easy to see that like how the user vector and item vector looks like. But the higher dimension, it will be difficult to visualize this information. Also, when we use any kind of distance metrics, suppose in this particular case, if we are using some kind of like cosine or L2 norm or all those things, we have to make sure that like we are taking into account the magnitude of user and item vector. Sometimes there is a case where user vector is very different than item vector, and in such cases, we will not have the consistency what we need to visualize those vectors similarity. So it's a much different case. Uh, what we would like to do is we would like to use some different techniques where we can use like a matrix factorization model where we can factor these vectors into different latent space, and these latent space actually can help us to apply those all transformations and different distance matrices what usually we cannot apply into your normal feature representation. So on the higher level, you have to understand that we have to sometime transform them into a different embedding, where on those embeddings we can apply those mathematical operations that are consistent on those embedding rather than using them into their raw form. And that is one of the reason that we use these different techniques. Uh, if you want to go more deep into that, like understand more like deeper mathematics, you have to think in a such a way that like comparing this line is most important, that comparing vectors from different types of spaces like Poincare or like hyperbolic versus Euclidean require careful consideration due to inherent geometric differences, because what geometrical understanding you have in the Euclidean space will not hold into like other different type of spaces. And in such cases, if you choose certain like distance metrics or similarity metrics, that will impact your uh, performance of your recommendation system. And that is the reason that like we don't we use like embedding spaces in most of the cases to bring them into like different kind of dimensionality rather than just apply those operations in the raw form. Okay, so again, like the another thing discussed here, like a feature based warm star. So feature based vector help us to also do some kind of warm start in certain scenario. uh, One of the scenario where we have a let's say we have like a we don't have like interaction data between user and item, suppose in the cold start process. In the cold start process we don't have like a explicit information about user and item embedding. In such cases what we do, we actually rely on extensive user input to create like user embedding. Now, to just explain into a very simple term, suppose you are building a recommendation system where you don't have any information about like this new user come to your platform and you have like no information about this user. What you know that like if you ask some kind of onboarding question to this user, you will able to obtain like some kind of feature representation of this user, right? So suppose you ask like some, you're creating like some e-commerce website, and you ask some onboarding question that what type of like shoes you like, or like what type of clothes you like, and all those things, and based on that you create like a user feature vector. And that user feature vector sometime can help you to compare with other user that how this particular user feature vector looks with other features, like other users like u2 u3, which are like who are already existing in your uh, database, or you have like certain type of items which are available to you, and you can compare those items to your users. So suppose you have I2 I3, so these items, this user feature vector can help us to identify that which are these items I should recommend to this user based on this user feature vector. So this is the process we call like warm start, and this is very important when you have like cold start problem. Uh, uh, how we can do it? Like we can integrate a user and item feature in our like collaborative filtering and metric factorization technique, where we obtain the uh, like let's say latent space embedding using the uh, feature vectors what we generate during the user onboarding. Uh, so sometime it has been seen that like what type of recommendation system we use. Uh, we have discussed about two types of recommendation system, where one we do have like lots of interaction data, like this bilinear factor model, and sometime we don't have like this uh, uh, available interaction data. So which one we should be using? The answer is like very different. It depends on your use case. I think in general practice, what we do for the cold start models, we use like this feature-based recommendation system, and for when we have like some kind of interaction data for like regular user, we use this collaborative filtering model. In the collaborative filtering model, we have to have some kind of interaction data with user, and in the cold start model, you can use like raw feature-based methods. Now, there is another way to obtain this feature-based method. One of the way is to find using clustering. And clustering is a very simple technique. What we do, like whenever a user onboards on our platform, we obtain some kind of feature vector, right? And based on that feature vector, what we trying to do, we have like some kind of segmented uses cluster, maybe some kind of unsupervised learning, where we have like certain kind of cluster 1, cluster 2, cluster 3, and what we are trying to do based on this feature vector, we trying to assign a cluster to this particular user. Suppose based on this feature embedding, this user belongs to this cluster 2, and now we can start making recommendations what this cluster 2 users are having uh, whenever we have this cold start problem. A very simple way that like someone is coming on our platform and like they rate that like they like shoes more than like let's say t-shirt. What we can do that like we can find out that who are the user who only bought the shoes and what type of shoes they bought historically, and based on that like we start like recommending those shoes to this user rather than like assigning this user to different cluster. Uh, there is another way to do that. We can also use some kind of tag-based recommendation system, like the tag-based recommendation system, where we try to classify tags of a user and item. Suppose you introduce a new item to your inventory, right? This is the IN, and you hire a team that create some kind of tags for these items. So suppose they say like this, the tags is like clothing, and then active wear, and suppose like something else. Uh, Based on this information, you have like some initial item characteristic of this item, and will using this information, you assign this item to a certain category where in the activewear category, this item will be recommended, or in the business casual category we should recommend. So this is another way to generate like some to create like some kind of initial feature vector to our user and item, so it can be recommended to a different set of users. Now, uh, combining this both techniques, we can use something called hybridization. In the hybridization framework, what we do, like we use these both type of model, that's feature based and so suppose you use a feature based plus matrix factorization or collaborative filtering model, right? So what we are trying to do, we are trying to uh, give this blend of these both model to our recommendation system. So one of the way like to combine these models is weighted combination of models. So we can assign some kind of weightage W1 and W2, and based on the this particular weightage, we'll decide that which particular model we want to use using some kind of standard Bayesian framework. We can also do some multi-level modeling where what we'll try to do, we can generate for initially for some segment of user, we can generate like some different ratings based on like some algorithm, and then once we obtain a rating, then we'll switch it to another level once user crosses certain threshold. So user starts with with the initial level of interaction. Let's say they only have only 5 interaction initially, so we'll only serve them feature based model. But once they have more than like 5 interaction, it will switch to metric factorization or collaborative filtering model. The third one is of feature augmentation. Uh, in this particular method, what we are trying to do, in even in the collaborative filtering model, we will try to obtain some kind of uh, uh, embeddings or like some kind of feature vector for our user based on some kind of learning we have, and with that feature embedding, we will try to recommend to our user. So simple example, suppose you have like this new item in, right? And this has a certain initial vector 00100, but we don't have like the embedding of this item. What we'll try to augment it to the existing item vector, which is let's say IE, and we'll try to augment it based on some features we have, or like some average of certain uh, columns and or rows, sorry, certain rows. And based on that, like we'll try to generate new embeddings, and this embedding now can be used for our collaborative filtering or metric factorization model. So as a rule of thumb, what you can do for we can use user and item feature based model whenever we have a cold start condition, but during the training we should rely on like metrics factorization or collaborative filtering models. Now what are the limitation of these bilinear model? So as the name suggests, these are like linear model. Now we know that like sometime it's a there may not be a linear relationship between user item and pairwise affinity. uh, so user and item don't have like any kind of relationship with the pairwise and affinity, the way they interact with each other. But we have to think in a like different way. What we are saying that there may be possibility that user item and pairwise and affinity do not have linear relationship, but there can be a possibility that there is a linear relationship exists between the latent factor, not the actual feature. So when we convert in them into a latent factor, there may be some kind of linear relationship exists there, and that is the reason that like we see there is a huge performance in mid-size recommendation system from this linear model compared to neural network based model, because there could be chances that in your latent factor you have like some kind of linear relationship exists rather, but not in your actual features. We have to be very careful in such cases. The second point also suggests that like when we can use neural network for non-linearity, but it does not guarantee the performance over matrix factorization. It has been seen in multiple times that like even if you use like neural network, it does not guarantee you will have like better performance over matrix factorization, because matrix factorization, even though it's a linear model, is a very simple model, and there can be it can utilize like linearity between latent factors. There are some challenges. Obviously, the first challenges is obtaining the user feature. Sometimes it's very difficult to obtain the implicit user feature. You can get like some kind of onboarding and all those things to collect as much as user information, but these most of the time these kind of like exogenous signals are noisy and limited, right? People might not come with like some kind of mentality where they just give the onboarding answers, but they do not stick with those onboarding answers. There will be a concerns of like onboarding friction, privacy, and security to obtain more user feature. The second thing, same thing about item. When you have like extremely large item catalog, it's very difficult to generate those like features for your items. It could be a lots of manual task, and like you have to do lots of tagging, which is not possible if you have like millions of content. In such cases, you have to rely on like the automatic feature engineering pipeline that generates high quality features. Um, there is a big problem of like separability sometimes in user and item feature. Sometimes you think that user and item features are like uh, completely independent to each other, but there could be some kind of dependence lies between, or correlation lies between user and item feature, which does not allow us to separate these user and item feature. And whenever such thing happen, that creates a problem, because here one particular feature is influencing another feature, and that might creates a problem when we do factorization, because in the factorization our objective is to generate uh, factors such a way that they individually like describe the relationship uh, in user, and individually describe the relationship of item. But it is not, it becomes very difficult when we have like some kind of this confounding relationship exists between this user and item. So sometimes and the fourth thing that like we are our hypothesis is that like our entire assumption is based on that the taste or preference is extremely personal, right? Whatever user is saying is extremely personal to this particular user, and whatever item uh, uh, is like a standalone define this item itself. But we all know that like humans are like social creature, and they have like there could be like some kind of internal shared experience network exists between two user can be like uh, can be liking a movie, right? And they could have like maybe different features, but they still like uh, so here we are thinking that just these features only will define the relationship between movie and the user, but sometimes it's not possible. There could be a like internal connection where a husband wife watching a movie together, they can like there's some kind of influence of husband, like just taking an example, right? Husband, some influence is defining what uh, his wife will watching with him this particular movie, right? So what we call it like sometimes these connections are like shared experience network that can influence the uh, uh, output of recommendation system or learning from the model. Now we go to the second type of recommendation system, which is called counting recommendation system. In this counting based recommendation system, what we rely on, like we rely on the count of a particular entity. uh, easiest easiest type of this type of recommendation system is this MPIR recommendation system, which is called most popular item recommendation. This is the very simplest recommendation. You just recommend popular content to everyone. So you have a certain type of a content catalog where you have like a certain items like I1 to IN, and you have like you know that like how many times this item has been washed. This item has been washed 200 times and this item has been washed like 5,000 times. You know that this is like more a popular recommendation. So you try to like recommend this one to lots number of user, and you recommend like a low engaged items to less number of users. Now that methods works when you have like certain constraint where you don't have enough information, but this method won't work for the all the cases, because first like we'll start getting the popularity bias, we will lose the recommend personalization aspect of it, and third, we will start creating a filter bubble or echo chamber where only certain items will be recommended to certain community. So to take this example, that suppose in this scouting based recommendation system, what we are trying to do, we are trying to optimize this click through rate, and the CTR is the simplest thing, that number of clicks per period of time. Now what we are trying to do here, like we are trying to uh, uh, so suppose this example is a great example. So suppose we have a we have a like a we have a content to recommend, right? So we have this xi content which we want to recommend, and this has like certain kind of catalog. This xi is is a part of like certain content catalog where we have like certain items, and we want to recommend this item for a particular time period, right? Suppose we have only one time available to recommend this content, right? We have only one shot. So someone comes to your like booking.com or like some hotel, or you want to recommend the hotel to this user, and you know that like you'll only get one chance. This user comes to your platform and you will not have any other chance to recommend this particular user again. What you will do in such cases, you will try to create this reward function such that you want to create you have like a certain time period C, and based on that certain time period, like you want to recommend this uh, item to this user X. Now in such cases, your reward maximization function always try to maximize the click through rate, CTR, and it knows historically that like certain item, like let's say item xi has highest click-through rate in the history. So what it's trying to do, it will try to recommend that most popular recommendation to the user. And this is like very constrained case where we are only talking about only one time, where we only have only like one time period available. And in such cases, we should stick with like, MPIR algorithm, which is most popular item recommendation, right? Now let's expand this case, because this is not the always case. Sometimes we get like, multiple chances, and we have like, multiple so in this cases, we only had one choice to just recommend our most popular content. But in the second case, what we have a different content. Like let's say here we have two content, P1 and PQ2. These are like not content actually; these are like more of kind of distribution. And based on this distribution, we have to recommend this users based on like historical and future uh, entry. So suppose this N0 is the like past visit of this user on platform, and N1 is the future visit of this future visit of this user on platform. And based on that, we have this expectation where what we are trying to do here, we are trying to recommend item to user, which not only depends on like the future recommendation of that user, but also based on the past visit of that user. And this equation helps us to identify that like based if we have like some kind of prior distribution of our items, we can actually uh, optimize this expectation. And how we do that, like suppose for in this particular example, suppose we have like normal distribution prior for a past user, and this is some kind of gamma distribution we have for the future uh, for the Q1, right? And here P0 is like our most like MPIR content, which is a high click-through rate content, but Q0 is like a different type of content. And we have seen that it is better to uh, use this approach rather than this approach, just sending like a most popular recommendation uh, to get like maximum expected reward. And although it depends on like some kind of prior distribution of our p0 and q0, but it this equation shows that like it is better to incorporate this like historical interaction of this user and the distribution of that content with some kind of prior, rather than just rely on this most popular item recommendation method. It's a little bit complex. I request you to go through the book to get more understanding of this technique, because it's very important to understand that like sometimes it's not uh, like we see in equation that it suggests that like it's better to generate higher expectation with like a blend of content rather than just sending like one content to every user. Now the third way to the second method in the counting based recommendation is called like correlation mining, where we try to obtain some kind of correlation between item and users to recommend our recommend content to user. So what we are trying to understand in correlation mining is that discovering the hidden connection between user choice and enhanced recommendation, right? What type of choices user made in past that are impacting its like his future recommendation. uh, in the item features, like we have like as already said, like we have some certain characteristic of item like genre or genre type to find correlation. uh, we are going beyond the ratings, because in previous chapters we only talked about rating, but here we are talking more about we are not only talking about rating, but we are trying to identify pattern and suggest in similar items, right? uh, we understand that how often two items like shows together, and that help us to provide more informed recommendation. And we will be using like we will not be like for this particular method, like we just first rely on like this creating this interaction metric is again, like if you remember, it is just simple like a user and item metrics, where if a user interact with a certain item, we assign it at 1, and if they don't interact with each other, we assign it as a 0, right? It's a binary matrix where we use this 0 1 notation to just um, uh, creating a this is also called like a incident metric, where we are just creating this metrics to understand interaction between user and item. Now what we are like what we can do, like we can expand this technique beyond the uh, two co-occurrence. So let's take this particular example for quick understanding, and then we'll go to the here, because this will become more complicated. So suppose you have like a certain user u, and the user is interacting with item xi, right? So you define this interaction as 1 if item I belongs to you, and 0 if it is not, right? Now you want to create this co-occurrence matrix. So what is this co-occurrence metric? This co-occurrence metric is nothing but just your like the interaction matrix and multiply by the transpose of that interaction matrix. So the transpose of the interaction matrix, what we discuss, uh, this can be called as I, right? So this is the interaction matrix, and if we multiply its transport with itself, we will generate this co-occurrence matrix. And what does this co-occurrence matrix says us that how many times two items appears together. So suppose, very simple example, suppose if you buy let's say some t-shirts or and there is a matching pants or like shorts available. So you try to understand that how many times it happens that once user buy this t-shirt, immediately they also bought this uh, shorts. And based on this co-occurrence matrix, we will understand that how many times this thing is happening. Now we can also create generate this basis vector where we just need like information of that particular I and j, that how many time like this I interacting with j, and if we multiply this basis vector with our co-occurrence matrix, we can find out that for which particular item we have like how many co-occurrence. uh, what does it do for us? It actually help us to create a like a aggregate level recommendation, where suppose you have like this add to cart method, right? So suppose you are on Instacart, Zomato, like any kind of food delivery service, and you add like, let's say, uh like Thai curry, right? And you know that like there is a co-occurrence matrix available which says you that like whenever someone orders a Thai curry or add to cart Thai curry, you immediately showcase them like, some brown rice or some, different vegetable or some soup, right? You know that based on your co-occurrence matrix that 90, like there is an, whenever someone like add orders a like a red curry, like they always order a like brown rice with it, or they always write jasmine rice with it, right? So this will help you to create those like uh, generate those recommendations for your user whenever you have like certain kind of co-occurrence happens. Now you can go beyond this like two pairs where you have like only two pairs, that how this two pairs, you can also do like three pairs, like once they do like what are the three items they do, or one they do four items they do. The only problem that it will increase the complexity of the system, and you need like better system to optimize such scenario. The simplest case we talked about, like here you can generate a co-occurrence matrix very easily with just using your like this interaction matrix. uh, uh, So employing this vector and matrix factor to co-occurrence count and identify top recommendation, and that is all objective of your generate using this correlation mining, where you can find out a correlation between like item and feature vector, and based on that interaction, you can generate a like a similar product. Okay, the second thing we want to use is here like point-wise mutual information, which is kind of uh, normalized version of co-occurrence model what we already discussed, but PMI actually help us to get the more information. So what is a PMI is heavily used in natural language processing, where we understand like, how these two words come together. Suppose let's say, I don't know, like some kind of word like iron ship or something, like they always occur together. So whenever iron and ship comes, like it is talking about like a metal rather than like, electronic equipment for your like, to remove the creases, right? So because iron has like two different meaning in English language, but you know that whenever iron comes with ship, it always means a metal rather than like, an electronic equipment. Or ironing clothes, whenever clothes come to iron with iron, it always represents an equipment rather than a metal, right? And that's why you remove the this ambiguity like from the like remove the ambiguity from the system by generating a PMI of this point-wise mutual information between two items. So suppose a PMI of two product can be represent using Cij. We already discussed what is the Ci. Ci is a co-occurrence matrix, total of interaction normalized by I and Ij. And why Cij is very different than the previous one? Because it is using this normalization technique. This normalization helps us to remove some kind of popularity bias, where one item is like, popularly like uh, one item has like a higher frequency than other item, and it might dominate the entire metrics. So that can be like normalized using this PMI. Now you have to understand that this PMI is not a distance metrics. And why it is not a distance metric? Because it is a distribution, and it is a distribution. Then if, uh, we learned that there is an axiom: any distance metric has to uh, uh, any distant metric has to obey that, it has to obey this triangle inequality, where x1 x2 should be less than and equal to x3, right? When we talk about distant metrics, it should always at the, sorry, I think I wrote it wrong, it should be greater than and equal to, right? So the triangular inequality says that, like, suppose you have a distance matrix x1 and x2, if the combination of both of them should be greater than and equal to x3. This relationship does not hold with PMI, and that's why we cannot use PMI as a distance metric, rather than we'll use it as a distribution. Now, one more important thing, that we can also have negative PMI. Negative PMI help us to understand that how often these two products or these two words don't uh, witness together or don't come together, right? So I already said, like, we can also use PMI to do add to cart method, where we have like certain elements available. We can so suppose you have x1, what you do, like, you can create like PMI with like all the existing items you have, like this x2 xn, and then you calculate the PMI, and based on like highest PMI, you can recommend this item with other recommendations. So uh, what are the like a different kind of similarity? As we already discussed that we cannot use PMI for similarity score, so what are the other similarity score we can use? So these are like this other similarity score we can use. One is the Jacquard similarity, which actually is a ratio of shared item of two user uh, divided by to the total item number of users. We can use this Sorensen dice similarity DSC score, which is a like extended version of Jacquard similarity. And we can also use this cosine similarity, which is very popular, which is a dot product ratio of dot product to the magnitude of individual items. Now, among these three, only Jacquard similarity has uh, like distance metrics property, rather than like these cosine and DSC. They both like all three have like interval between 0 and 1, but like cosine has -1 to 1, because we know that whenever something is a -1, that means that they are they are representing a negative rating. They are they are not coming, they are not similar, they are highly dissimilar. uh, it can also accommodate the cosine similarity, can also accommodate thumbs up and thumb down by mm, extending the direction, because these are like these are applied on set. So these are applied on uh, discrete values, where you can apply cosine similarity to continuous value also. And there is a relationship exists between Jacquard and dice similarity, which can be represented with S is equal to 2j plus 1 plus j. That means that once you know one similarity score, you can obtain the second similarity score. So these both are like interdependent. So as we know that how the similarity work, so for the similarity, why we use similarity? First, use of similarity, that it help us to understand the measure of closeness as a similarity between two items, right? It help us to find out neighbors in items in user space. So it help us to understand that like which particular user is similar to another user, and which particular item is similar to another item 1 and item 2. uh, we can also rank this recommendation based on the nearest neighbor we have. So suppose for this particular user, if we have nearest neighbor, like say item 1, item 2, we can actually draw like certain circle to find out like which neighbors are nearer to which neighbors belong to this particular circle, and based on this neighbors we can recommend to users. We can three ways we can use this similarity. One, we can do user similarity. So you find a user who has similar taste like you and recommend. So I'll take the very simple example, Netflix example. So suppose you have like you are user one, and you have your friend user two, and you that you are very close to your friend. So if your friend you like action movies like M1 and M2, uh, and your friend only watched M1, you can recommend M2 to your uh, user two. So this is the one way you do like user similarity, because we found out that user one is similar to user two. Similarly, we can do item similarity. You have item one, item two. You know that this item has been watched by user one, user two, user three, and user one and user two both watch this. Like user one watched this item, so you can also recommend user two this item. This is again item similarity, because here you are finding a similarity between item and item. And third is like very simple, user item similarity, where you find out the compare the interest with characteristic of new item you seen, good match. So suppose you find a good genre of the book, and this genre is slightly coupled with you, that you like this genre, and you find another book, but he or she also like this particular genre. So what you do, like based on this connection, you recommend this book to user because you both like a same genre. uh, yeah, so on a very high level, what we are trying to do, we try to query our recommendation based on your interest. And can so you what you query is like uh, find out the interest of your user and generate a candidate, that means the items for your particular user. And when we have like lots of recommendation, like to make lots of recommendations system, what we can do, there are some kind of computation tricks we can use to increase the performance of this recommendation system. The only problem is that we have seen that whenever we talk about feature and item based recommendation system, the biggest problem with both of these recommendation system is the dimensionality. Because if the user, we have high amount of user where we have large amount of features, and or we have large amount of items with large amount of feature, the dimension is so big that like sometimes it will be very difficult to compute such metrics. And these matrices are becoming like order of like n cube or n square operation, o n square or o n cube. And in such cases the computation become extremely difficult. To to get away with this computation problem, we go with like low ranking method. Today we'll not have time to discuss about low rank method, but we'll discuss in the next chapter. But in the next chapter, we'll explicitly talk about low rank method for optimization, where we try to overcome this problem of user and item feature, and we'll generate like a same recommendation, but with some kind of approximation, because there is a trade-off whenever we lose some kind of information there. So with that, I stop the recording. Thank you so much, and see you next time for chapter 10 and 11 to learn more about low rank ranking and metrics of recommendation.